Now maybe Professor Mykhailo Zarichnyi maybe can start. He will talk about invariant star measures.
Thank you very much for introducing me, and I would like to start with my thanks to the organizers of this conference, which is a traditional conference and which is one of the main events in the area of geometry and related topics, not only in Ukraine, but also in, let me say, in the whole world. I would like to share my screen if possible. How to share my screen? Oh, it's okay. Well, this is, do you see my screen?
Yeah,
no,
I hope so.
No,
Yes, yes.
Now.
Oh, it's correct.
Yes.
Thank you. So you can see that this is a joint talk with Natalia Mazurenko from the Precarpathian Vasil Stefanik University, and the title is Invariant Star Measures. And I would like to start with some definitions, but one more remark about organization. When we prepared our talks, not only we with Mazurenko, but also Kristina Sukhorukhova, we realized that there is a non-trivial common part of this, introductory part of definitions and so forth. Therefore, Kristina asked me to announce some of her results, and I will do that, and her talk will be skipped today. So I will start with the following definition, that of a triangular norm. This is an important notion from the theory of so-called fuzzy metric spaces. And a triangular norm, in other words, a T-norm, is a continuous, associative, commutative, and monotonic operation on the unit segment, which is denoted by I, the segment 0, 1. And for this operation, 1 should be the unit, its unit, the unit. Well, we know what is continuity, associativity, commutativity, and monotonity means that A star B is less than C star D if A is less than C and B is less than or equal to D. And the following are very important examples of the triangular norms. So the first one is merely a multiplication. A star B is A multiplied by B. Another definition is, another example of a triangular norm is that of minimum of A and B. And we also consider a historical example, which is called the Lukashevich T norm. This is the following: A star B is maximum of the following two numbers, A plus B minus 1 and 0. Actually, the notion of triangular norm, it serves as, say, for adding things that cannot be added. Like, one cannot add two probabilities because the probability cannot be greater than 1. So instead of addition, one should use more complicated, more sophisticated operations, and the choice of T norms, of a complete T norm, depends on the context. Well, and given a triangular norm, we define the following notion. Let X be a compact Hausdorff space. A functional mu, which acts on the set of continuous functions from X to Y, and its values are in I, is called a star measure if the following holds. First of all, this functional preserves the constants, namely its value on the constant function with value c is equal to c for every c in the unit segment 0, 1. The second property is that it's a star homogeneous, namely if we consider a constant lambda, a number in the interval, and if we consider the operation of this lambda with a function phi from this set, this lambda star phi means pointwise operation. Well, a number acts on a function phi. So the value of mu on this new function should be equal to lambda star mu phi. And the third property is that mu preserves the maxima of all the functions. By wedge, I denote the maximum of two functions, pointwise maximum or a maximum of two numbers on the right-hand side. For every compact Hausdorff space X, the space M star of X of all star measures, which is endowed with the weak star topology, is compact. This was proved by Sukhorukova, and now the publication exists as a preprint. And what is a weak star topology? Every star measure is a functional, so we say that a sequence of measures converges to a measure if there are values on every function converge to the value, if the values of the elements of this sequence converge to the value of the limit measure. Usually, it's a traditional definition of the weak star convergence. And let me consider an example. A simple example of a star measure is the following. Let us consider a finite number of numbers from 0, 1, and we suppose that their maximum is equal to 1. And let us choose points x sub 1 up to x sub n in this space X. One can define a star measure as follows. Mu of f is the maximum from I from 1 to n, lambda sub I star phi of xy. And we obtain a star measure. It should be, we used asterisk, the name asterisk, but star is better. So a star measure. A star measure, which is the maximum of lambda I star, the Dirac measures concentrated at x sub I. Well, so a combination of Dirac measures, a star combination of Dirac measures. And Sukhorukova also proved the following, that if we have a continuous map of compact Hausdorff spaces, then it induces the map of the spaces of star measures. This map is denoted by M star of F and X by the following formula. We do not have a formula for that, but it disappeared somewhere. M star of F of mu should be the measure should be an adjoint operator. Every map f from x to y determines a map on functionals in a natural way. And this obtained map is continuous, is known to be continuous, and in fact we obtain a functor acting in the category of compact Hausdorff spaces and continuous maps. It turns out that similarly to the case of probability measures, one can define the so-called Barnsley-Hutchinson operator for for star measures. It works as follows. If we have a finite family of functions of self maps from X to X, and if we have a star measure on the set of indices, namely the set of 1, 2, 3 up to n, so we see that this measure should be of the following form. The maximum of lambda I star delta I, delta sub I, where I is here in this set. Therefore, one can define the operator, which is denoted by phi capital, from m star x to m star x, which acts as follows. Phi of mu is the maximum of lambda I star, the image under f sub I of mu. A measure, a star measure is called invariant if it's a fixed point of this operator phi. This definition of invariant measure is absolutely analogous to the definition of invariant measure due to Hutchinson in his famous paper about fractals, which was published in Indiana Mathematical Journal. The existence result of Hutchinson is derived from the Banach contraction principle, which means that every contraction map has a unique fixed point. But recently, we with Mazurenko proved that actually we invented a proof which does not rely on the Banach contraction principle. And it turns out that this proof can be modified so that it works for invariant measures, and this is our result. But I would like to mention also the metric approach. Actually, recently in 2021, these authors, D'Acunha, Oliveira, and Strobin, they published a paper. They published a preprint. It doesn't exist as a paper, in which they modified the so-called Basilevich-Repouche and Zarichnyi metric as follows. On the set of idempotent measures, they modified this, and I would like now to define this metric for the star measures. So given alpha, a number between 0 and 1, strictly between 0 and 1, we consider the following pseudometric on the set of star measures. So we define d sub alpha of mu nu as the supremum of the absolute value of the difference such that phi is a non-expanding function. Or Lipschitz function with constant 1. And now, given two star measures and two constants, two parameters, well, we define the metric d tilde sub alpha q as the sum, where I is an arbitrary integer, and well, this should be not I but n here, I'm sorry. And well, we obtain such a series. And it turns out that if our iteration function system, I mean the collection of our starting functions f1, fn from x to x is Banach contractive, which means that they are Lipschitz, and the Lipschitz constants are less than 1. Then the map phi is a contraction with respect to the defined metric, which allows us, to produce, to apply Banach contraction principle and obtain the invariant measure. I would like to mention some applications of these star measures. First of all, it concerns convexities. Taras Radul recently mentioned the notion of maximum star convex sets. In order to give a precise definition, it would be necessary to develop a theory of monads and algebras. I don't have time for that. So let me simply mention this fact that having the notion of a star measure, one can define the notion of so-called maximum star convex sets, convex set, and the convex sets that are that correspond to the so-called idempotent measures. They are the maximum plus convex sets, which are related to the so-called tropical convex sets, and there is a special area of mathematics called the tropic geometry. Well, so briefly, every triangular norm generates a convexity theory. Another application is that to the equilibrium theory in game theory or mathematical economics. Also, I would like to mention a phrase from Radul's paper that the convexity structures are widely used to prove existence of fixed point in equilibria. Let's consider a star measure game. This is the following game. Player I chooses a star strategy, which is a point of m star from x sub I. And given a payoff function defined on xi, one defines the payoff function u tilde sub I, which is defined on the product of two spaces of star measures by the following formula. So, and this operation of tensor product is, its definition is similar to the tensor product of probability measures. I don't have time to define it. But I would like to say that these game theories are useful to model strategies which are not linear, because human behavior is not linear. It's more complicated, and one should use more and more sophisticated notions of measure to have the corresponding equilibrium theories. This is about future possible generalizations of these measures. And I would like also to consider the ultrametric case. So given a positive number r, we denote by f sub r the set of all functions which are constant on the balls of radius r. This should be on the ultrametric space. Well, I skipped this slide. A metric D on X is called an ultrametric if it satisfies the following strong triangle inequality. And together with Kristina Sukhorukova, we constructed an ultrametric on the set of all star measures of finite support of an ultrametric of compact supports. should be compact here, on ultrametric space is introduced. And this introduced ultrametric is a counterpart of the so-called Hartog-de ultrametric on the set of probability measures, and the Hubble ultrametric on the set of idempotent measures. The first ultrametric was used in the theory of formal programming languages. So I hope that our metric would also be of some interest. And this is the definition. Given a positive R, we denote by F sub R the set of all functions which are constant on the balls of radius R. Then d tilde between mu is the infimum of R, such that the values of this mu and nu coincide on all the functions which belong to F. Well, and similarly as in the paper of Mazurenko and idempotent ultrametric fractals, one can prove existence of invariant star measures on ultrametric spaces for the Banach contracted IFSs, iterated function systems. And here we have a picture. The picture is taken from the paper of the mentioned authors. This is a picture for an invariant ultrametric on a Cantor set, which can be endowed with a natural ultrametric. And also I would like to mention then an intermediate notion of K ultrametric, which is introduced by Savchenko, Alexander Savchenko. A metric D on the set X is called a K ultrametric, where K is a non-negative number or infinity if the following strong triangle inequality holds whenever, not for all x, y, z, but whenever the minimum of these two distances is less than or equal to k. Well, and it turns out that the hyperspace, which means the space of all compact Hausdorff compact non-empty subsets of a metric space, and this hyperspace should be endowed with the Hausdorff space, with the Hausdorff metric. So it should be also Savchenko proved that the hyperspace of any K ultrametric space is again a K ultrametric space. And we use this fact and the identification of any star measure with the subgraph of its density function to define a K ultrametric on the set M star of X for an ultrametric space X. And it's a good point to stop here. And thank you for your attention. So as I told you, as I also, in addition to our results with Mazurenko, I mentioned the results of Sukurukova and Alexander Savchenko. And well, so that's it.